Hi guys, there's actually an issue. Just realized it. Gia, you still have to sign the Lawrence Professor part of the Ehrenfest wall.
I signed it.
No, you signed the Ehrenfest wall, but there's a separate section that is more prestigious.
No, I signed actually both.
Oh, you signed them both.
Yeah,
You
yeah,
someone
that's
managed.
right.
Somebody helped you out. Great.
Yeah, that's
Yeah,
right.
because you have to be physically present for that. And such a
Right.
right Munich.
But in any case, otherwise I'll sign it separately.
Okay.
So you took care of that, Alexa. Who did it?
No, I didn't do this. Someone else did it, not me.
It was my mistake, Jan.
Oh, you did it, Anna, but it's great, you know. It had to be signed anyhow, and I couldn't be there because I was forbidden to show up, right, in the building.
Yeah.
So you took care of it. I don't have to worry about it. I will check out Gia's name when we open up again.
Very good. So with this optimistic information, let us start. So we have today the third Lawrence, I would say, Lawrence lecture by Gia Dvali. And today the subject is the cost of altering gravity. So Gia will explain us why is it so non-trivial to modify gravity.
Okay. Hi everyone. Can you see me actually?
Yes, we can see.
Yes. Okay, because I don't see myself, so I don't know what's happening.
Everything is fine. We see you, and we can switch between slides. And
okay, very good. Hello everyone. Again, it's a great pleasure to give this talk. So I was invited by Alexei, suggested to that there is some interest in modified so-called modified gravity story, and this is the idea that we came up with our group at the NYU beginning of 2000 with Gregory Gabadadze, Massimo Porati, Cedric Defaye, and so on. And I worked on this for a few years, and yeah, I'll be happy to share my understanding of the story. So first of all, so this is supposed to be very pedagogical and also informal. So of course, if you have any questions during the talk, please don't hesitate to ask. Also, if there will be some technical questions, I can explain later technicalities. Now, first of all, we can ask this question: what is gravity? Now, gravity, the way we know it, starts from Newton, and this is the famous Newtonian potential, gravitational potential between two masses. Now, already in Newtonian gravity, you can think in terms of a virtual mediator, despite the fact the theory is classical. And for example, this is the equation, as you know very well, this is the equation for point mass, Poisson equation. And the solution is Newtonian field that is produced by this mass. Now this Newtonian field, phi, is controlled by a very important length scale, which is called gravitation, which we call gravitational radius of the body. So this is sometimes, or Schwarzschild radius sometimes. So this is Newton's constant times the mass. There is also a factor of 2 there. Now in many places, I will just keep this factor of pi's and 2's, etc., where they are not important. So therefore, so in Newtonian physics, a source produces a gravitational field, and then this field acts on different other sources. Now, again, this can be understood already at the classical level. If you simply, because this is an equation which has Green's function, and you can think of this as a propagator, of course, in quotation marks, of a mediator. So there's a mediator, a virtual mediator. And you can even write down a Feynman diagram for Newton's potential, in which you have masses and the virtual mediator. Of course, at that time there was no concept of graviton. Today we call it a virtual graviton.
So yes, this is so far just a formal mathematical solution of Poisson equation in terms of Green's function. You just interpret it in terms of virtual mediator.
That's exactly the point. Yes, exactly. So now the reason why, as I will discuss into transparencies. Of course, the same is true in Einstein theory.
Yeah. That's my question. When you do Einstein theory, it's basically like the Newton force is like a Coulomb force electromagnetism, right?
Exactly.
So it's literally like in the propagated Einstein theory.
Exactly. That's exactly right. So therefore, we have this concept of the field. There is a source which generates a static field, and the static field acts on the other sources. It's all classical, of course. Now, next step is Einstein's general theory of relativity. Now, Einstein's theory of relativity represents a completion of Newtonian theory in two directions. First, towards relativity, it makes it relativistic, meaning that now Einstein's theory describes motion of arbitrary fast-moving sources and unifies space and time. But basically, it makes gravity invariant and the theory of gravity invariant and the Lorentz transformations and Poincare group. And on top of that, it takes into account nonlinearities. In other words, it takes into account self-influence of the gravitational field, because gravity itself gravitates. Now, Einstein theory, as we know very well, is a theory of a dynamical metric, G mu nu, traditionally called. And there is this famous Einstein-Hilbert action, where R is Ricci scalar and minus G. Of course, this is a textbook material, everybody knows about it, determinant of the metric. And plus there is an action of anything that is not gravity, so we call it matter. Now, from here we have these famous Einstein's equations, which in particular we can rewrite in terms of Riemann tensor. Now, T is just a trace of energy momentum tensor. So in Einstein theory, whatever carries an energy or momentum, which means everything, because in physics, we cannot have a physical entity that doesn't carry energy or momentum. So therefore, everything gravitates. So now, again, now we have this concept of the gravitational field, which you can think in terms of geometry. So you have a source and another source. For example, you can have a heavy source and a lighter source. So the heavy source could represent, let's say, a sun, and lighter source could be Mercury. And source creates a gravitational field around it, and then this gravitational field acts on another source. So therefore, a probe moves according to geodesics in the metric, which is controlled by the metric that is created by a heavy source. Of course, in reality, everybody contributes into creating metric. Now, it is very useful to analyze gravity in so-called weak field regime. So in weak field regime, what you do, you split metric into a background metric and small perturbations or small deviations from the background metric. Now, in most of the places in the universe, in our real universe, in most of the places, you can always go into a convenient reference frame in which this background metric is Minkowski with a very good accuracy.
Yes.
The exceptions are if you want to consider gravity of the universe itself, because we don't really live in Minkowski universe. More likely we live in the De Sitter type universe. or for example, if you are near black holes, etc. Okay, so otherwise, typically, you can always find a good reference frame in which the deviation from Minkowski metric created by the source is small. For example, the example is Earth's gravity. Now, of course, metric is not an invariant object. That's a metric is gauge dependent. So, for example, in general, if we are on the surface of the Earth, we are influenced by gravity of the entire universe. But normally we don't care about this. We can always go into a smart reference frame, and that reference frame is simply when we, together with the Earth, are freely falling in the gravitational field produced by the rest of the universe. And so, therefore, we can analyze influence of Earth's gravitational field in this reference frame. And the deviation that is created by the Earth's gravity is very small. It's approximately 10 to the minus 8, 10 to the minus 7, something like that. In other words, this is another manifestation of the fact that Earth is very far from being a black hole. Okay, so now once we go in this weak field approximation, we can write down linearized. We can linearize Einstein's equations. Now, this is what represents the linearized Einstein's tensor. Okay, has this pretty beautiful structure. Looks a little bit complicated from the first glance, but actually it's a pretty nice structure. And at the linear level, there is gauge redundancy, which is simply a remnant of general coordinate, general covariance. So this redundancy is telling us that we can change graviton field, the linearized gravitational field, by a symmetrized derivative of a vector. Now we can fix the gauge. For example, let me fix this gauge, and in fixing the gauge, we can write this equation in more useful form. So it's in this form. It's sort of almost it's D'Alembertian. It's not Poisson equation. It's not Laplacian, but it's D'Alembertian. But this is linearized equation that is, of course, relativistic. Sorry, is there a question? Okay. Now, in this language, of course, again, we have exchange of, so if the force or mediated between two energy momentum tensors, again, we can interpret this as an exchange of a linear metric perturbation. Exchange of a graviton. Now here we already can use the name of graviton. And again, here immediately we can, this is again textbook material, we can recover Newton's law. For instance, if you take a non-relativistic source, then we can do a further reduction of this. So first we took linearized limit, weak field limit, and now we can take non-relativistic limit, and then recover Newtonian equation. So now, again, but there are now other effects. For example, deflection of light by sun, starlight by sun, this famous effect. So again, now we can understand that also as graviton exchange. That was not possible in Newton's theory because Newton's theory was non-relativistic. But in Einstein theory, that is possible already at the linear level. Now, there are a few scales of gravity, and I will use units c equals 1, and then later also I will take h bar equals 1, Planck constant equals 1. So the first length scale is an extremely important length scale, which is a quantum length scale, is Planck length. We can form something that has dimensionality of the length square by multiplying h bar by Newton's constant. So Planck length is approximately 10 to the minus 33 centimeter, is minuscule. Correspondingly, there is Planck mass, It's approximately 10 to the minus 5 grams, 10 to the 19 GeV. Now, okay, from now on, I will set h bar equals to 1, because I just wanted to demonstrate that both concept of Planck length and Planck mass, they are quantum. So when we take limit in which h bar goes to 0, Planck length goes to 0. From now on, I will set h bar equals 1. And so now we can rewrite metric fluctuation in terms of a canonical normalized graviton field. Okay, so from now on, I will use the power of effective field theory thinking. Now, effective quantum field theory tells us that as long as you identify correctly degrees of freedom, and as long as degrees of freedom are weakly interacting, we are fine. We only have to start, we only have to worry once we go beyond the domain in which degrees of freedom are weakly interacting. So once we hit strong coupling, then we have to worry, and the corresponding effective quantum field theory description, effective QFT description breaks down. But as long as couplings are weak, we are perfectly fine. So what are the couplings of gravitons? Okay, so gravitons gravitate. They self-interact.
Sorry, Gia, by we are fine, you mean that our theory has predictive...
you can do calculations.
Yes.
We are fine means that we can work with the theory. We can do well-defined calculations. As long as degrees of freedom are weakly interacting, we can use perturbation theory and so on. Okay, so the theory is we can work with it. I will give some examples. Now, so first thing therefore, in order, before we declare whether we can work with gravity or not, okay, at which curvatures, at which energies we can work with Einstein gravity, first we need to identify whether gravitons, what is the coupling of gravitons, and in which regime are gravitons weakly interacting. Now, gravitons, of course, self-interact. Gravitational field self-interacts. And so the vertex is proportional, is suppressed by the Planck mass, and is proportional to the momentum transfer in the process, always. And so, and correspondingly, the graviton coupling is, I call it alpha gravity, is given by square of the momentum transfer and divided by m Planck square. Now, so now we have processes in which gravitons participate. Most of the cases that I will discuss will be classical. This means that in those cases, what you have is not individual graviton quanta, but gravitational field. But gravitational field, for instance, gravitational wave, also represents a coherent state of gravitons. So you have high occupation number of gravitons. So in general, so the story is that if the wavelengths of momentum transfer, the Broglie wavelength of momentum transfer in a given process, or curvatures are so if curvatures are given by so in other words, so to put it differently, so if you have a certain situation, for instance, you have some collision of gravitational waves, or you have some collapse and formation of a black hole, or whatever, right? So there is a gravitational process in which you have some momentum transfer. So typically this momentum transfer is controlled by the wavelength of gravitons in the problem, and by the curvature. So if the wavelength of gravitons involved in scattering, or the curvature involved in scattering is small, correspondingly the momentum transfer is also small. Okay, so you can use them, you can replace them in order to measure whether gravity is weak or strong. So therefore, so you can think of gravitational coupling as the ratio of the Planck length to the typical wavelengths of the gravitons involved in the process, okay? Not of the free gravitons. Of course, free graviton you can boost by going to arbitrary reference frame. I'm talking about interaction. I'm talking about the Broglie wavelength of the momentum transfer in an interaction, or the curvature, okay, again. So therefore, gravity is a well-defined effective field theory as long as the curvature radius is much larger than the Planck length. Correspondingly, the momentum transfer in the process is much lower than the Planck mass. So that's why Einstein gravity works in most of the places in the universe, because in most of the places in the universe, we don't need to encounter processes with Planckian momentum transfer or Planckian curvatures, okay? Now, for curvatures less than Planckian, actually, Einstein gravity is not any worse, and in fact is much better than any other effective field theory, quantum field theory. For example, chiral Lagrangian or Fermi theory. Chiral Lagrangian is also not renormalizable, but we can work with it as long as we are at this scale well below the QCD scale in that case, right? Or Fermi theory, it's the same thing. I mean, Fermi theory is not renormalizable. Actually, Fermi theory is worse than gravity in a certain sense. But we are working with it, and we can do computations. Now, to really make this comparison, just to I'm talking. These are known things, of course, but I'm just setting up the stage. Now, for example, let's compare interaction of, let's say, two electrons, or E plus E minus, let's say. Let's say you scatter E plus E minus by photon exchange at 1 centimeter distance, right? The corresponding electromagnetic coupling constant is 10 to the minus 2. Whereas if you compare the similar distance at the scattering of two gravitons at the similar distance, let's say at 1 centimeter, let's say I take two gravitons of 1 centimeter wavelength and I scatter them at one side for inverse centimeter momentum transfer. The corresponding coupling is 10 to the minus 66. So obviously, this is theory that is infinitely weaker interacting than electrodynamics. Now, what about gravitons that contributed to dynamics of the solar system? Okay, so here we can talk both about virtual gravitons or real ones. So there are virtual gravitons that contribute to the dynamics of the solar system, and they are wavelength of the virtual gravitons which govern dynamics of the solar system, for instance, Keplerian orbits. Their wavelength is larger than 10 to the 13 centimeter. So correspondingly, for such gravitons, the gravitational quantum coupling, gravitational coupling, is 10 to the minus 92, if I estimate it correctly. So now you can ask, right? So you can say, well, wait a minute. If graviton coupling is, if the couplings of gravitons that govern the evolution of the solar system is so suppressed, how come nonlinear effects, which precisely come from graviton-graviton interactions, can still be important or measurable in solar system? For example, the perihelion precession of Mercury. The answer is very simple. The reason is because Sun is very heavy. So Sun is so heavy that it compensates this suppression by the weakness of individual gravitons. Let's see it explicitly. Now, the Schwarzschild radius of the Sun is approximately a kilometer, 3 kilometers or something. So approximately 10 to the 5 centimeters. So this is gravitational radius of the Sun. This is what I'm defining it here. So it's not an actual radius. This may, don't get confused with this notation. It's not an actual radius, it's a gravitational radius. Now, for example, let's think about perihelion precession of Mercury in terms of classical Feynman diagrams, okay? Now, of course, at the end of the day, these Feynman diagrams, if you compute them literally by using all the rules, they will simply give you the classical result. Why? Because there is no emission of on-shell gravitons in this process. So all the sources at the end of this diagram are classical. So this corresponds to the fact that the gravitons that are sourced by the sun, so this is sun, so sun sources gravitons, and the gravitons that are sourced by the sun, they also source themselves. So before sourcing Mercury, they source themselves once, and this is the leading nonlinear process. Okay. Now you can easily count, because there is L Planck appearing at every vertex, but then it's accompanied by the solar mass, and solar mass is enormous. Graviton interaction of gravitons themselves is, of course, extremely suppressed. Why? Because the typical wavelengths are given by the Sun-Mercury distance, and here we have Planck length, and so this factor is 10 to the minus 46. Okay, it's extremely suppressed factor, because Mercury orbit is 10 to the 13 centimeters. So the effect, however, because we have sun here, which is very heavy, it compensates. And so at the end of the day, the effect, of course, is given by, we can combine simply these factors. Gravitational radius square of the sun divided by the actual distance, Sun-Mercury distance. So the relative correction to the linear, so linear would be square root of from here, right? So the relative correction to the linear effect is only 10 to the minus 8. So it's not, of course it's suppressed, that's why perihelion precession of Mercury is a small correction, but it's not enormously suppressed, because it is compensated by the fact that sun is very heavy. Now, if you would instead ask what are the corrections to Mercury perihelion precession, let's say, because of actual quantum gravity effects, for example, emission of graviton or things like that, of course the effect would be humongously suppressed, would be 10 to the minus 92. Now notice the following thing, and this is pretty useful, that the effect, which is nonlinear correction, classical nonlinear correction, actually you can represent by using trivially relation of the Schwarzschild radius, you can trivially represent as the quantum effect, strength of the quantum effect, alpha gravity, times this ratio, times the ratio of the solar mass squared divided by Planck scale square. So we get a very nice expression. So we get that quantum classical correction is proportional to quantum correction, a would-be quantum effect, times, but the proportionality factor is enormous. It's solar mass squared divided Planck scale square. This is this factor that actually makes Mercury perihelion observable and not suppressed. Therefore, this is very important. So we have to distinguish between two different things, and this will be also very important for modified gravity. We have to distinguish between two corrections. So corrections that come from nonlinear corrections, which come from macroscopic heavy objects, these objects that are much heavier than the Planck mass, and they have gravitational radius, which is much larger than the Planck length. And these corrections, they go as ratio of the gravitational radius to a distance in the problem squared. This is classical correction. But then quantum corrections, they go as quantum coupling, and they go as Planck length squared divided by the actual distance squared. And these two corrections are very different for macroscopic objects. So this is the general rule. For any source, this works. So if you have, for any planet, for instance, or galaxy or whatever, so if you are interested in this ratio of quantum to classical effect, it is going as the mass squared divided by the Planck mass square. So in general, if you are interested in planetary motion or astrophysics, sources heavier than the Planck mass are classical, or sources which have gravitational radius much larger than Planck length are classical. Now, I want to avoid the confusion. Yes? Yeah, I'm listening. Is there a question? No? Okay. Now, I want to avoid confusion. The converse is not always true. So for example, you can have objects that are much lighter than the Planck mass, but they are all still classical. In fact, Planck mass is the mass of a cell, a biological cell, or something like that. So of course you can have objects that are lighter than the Planck mass, but still behave classically if they have high occupation number. For example, radio waves. You can have radio waves with energy which is much less than the Planck mass, but they can still be described classically very nicely because they represent coherent states of high occupation number. But so now in general, if I have an object which is compact, which is heavier than the Planck mass, as is compact enough, then the nonlinearities become 100% important around its gravitational radius. For example, for black holes. Black holes are example of that. So to summarize, so in Einstein's GR, if we have this macroscopic system, the quantum corrections are very small, irrespective of nonlinear effects. Nonlinear effects could be very large. And again, the example is a solar mass black hole. For example, if I take a solar mass black hole and I ask how important are quantum corrections to horizon geometry, okay, they are suppressed by alpha gravity. They are suppressed by the factor 10 to the minus 77. In fact, you can immediately tell this by remembering about Hawking radiation. For example, this is Alice, and she's watching a solar mass black hole. And now if you have a solar mass black hole, it evaporates precisely because of the quantum effects, right? But actually it takes precisely 10 to the 77 Hawking emissions in order to reduce the black hole by half, the mass of a black hole by half. So this immediately tells you and illustrates what I'm talking about. So that's why black hole lifetime is enormously large, because the effects that give decay of a black hole, they are quantum, okay? And they are extremely suppressed. For example, solar mass black hole would live like 10 to the 82 centimeters, and that's enormous, the lifetime. Now, the thing is that the story is very different in large distance modified gravity. If you try to modify gravity at large distances, it turns out that the story changes dramatically, okay? Now, by now, we can define gravity. Now, our definition of gravity will be whatever mediates force between two energy momentum tensors, okay? So gravity, I would call gravity anything that is sourced by energy momentum tensor, okay? Now, in Einstein theory, the mediator between two energy momentum tensors is Graviton, which is a massless spin 2 field. And the question is, what are the alternatives? Now, let me discuss briefly, mention what could be motivation. So you can ask me this question, why are we doing this?
Yes,
and what could be motivation for modifying gravity at large distances, because it works so well?
Yeah, it seems that there is a question.
Yeah, sure.
Just before you go any further, so what do you ask of the energy momentum tensor? Is there some, I mean, what do you call an energy momentum tensor? Anything that
is well defined. I mean, you want to talk about energy momentum tensor of matter, for instance. It's a Noether charge for the system. So here I'm, as I said, we are choosing the background to be Minkowski for simplicity, right? And so then asymptotic states, I can control them by Poincare symmetry.
No, then the question's clear. Thank you.
Okay. Yeah. Right, but thanks for asking, because maybe I should reiterate. So, in most of in this talk, in most of the time, I will be in asymptotical Minkowski space, and that also gives it also gives this power of use Poincare symmetry as a tool. Now, the original motivation was that we had in 2000 with Greg Cavadaz and Massimo Porratti was to explain accelerated expansion of the universe. At that time, the accelerated expansion was discovered, and okay, we were thinking that okay, maybe it can be explained without introducing any dark energy because of modification of gravity. We call this idea sort of so-called self-acceleration. And then we had an explicit model that was fully nonlinear and generally covariant. And so it was a very concrete framework to explore this idea. And okay, there were later other papers with Cedric Defaye, Mike Turner, and others. And then there were also other groups like Harold et al. Later they came up with sort of so-called F of R framework, F of R gravity. Sort of upside down inverting this so-called Starobinsky model. But I will not enter there because I will discuss general aspects. I will not go into model building. The second motivation was the so-called idea of degravitation. The question was, if we modify gravity, whether vacuum energy could gravitate differently than other sources, and maybe this somehow can give some idea of about smallness of vacuum energy and so on. And of course, finally, there could be why not, what if questions. I mean, now I will not enter into model building, although the consistent models are very few, if not zero. The number of consistent theories is extremely small, maybe even zero, as we will discuss. But I will try to focus on generic aspects of the story, of certain generic aspects. Unfortunately, one talk I cannot cover everything. But now the first question is, if you want to modify gravity, the question is how to parameterize, because naively it looks like there must be a plenitude of theories. So there must be like an enormous number of possibilities. This is a very naive view, but let's say you start with this view. And you say, okay, but how can I parameterize this modification? Now, the way I will parameterize this modification is through the dispersion relation of long wavelength gravitons, okay? So, in other words, here's the procedure. So you have theory of modifying gravity. And then I'll tell you, okay, go to a distance so this is sufficiently large. Let's say, take two sources that interaction among the sources are mediated by this modified gravity, and take the sources far apart or make them spread far apart, so that linear theory is valid. Okay, so that you are in weak field approximation. I mean, any theory should have such a limit. Otherwise, it is not understandable as effective field theory. Then I don't know how to work with it. And actually, nobody knows how to work with it. So, and then go to those distances, then linearize the perturbations. Again, I say I use Minkowski as an asymptotic background because I come from particle physics, from S-metrics, and so therefore this is extremely useful to use Poincare symmetry for parameterizing this. And so I will call this modified graviton H tilde. Now, then the question is, what kind of dispersion, what kind of linearized equations this graviton satisfy? Okay, and it turns out that there are three basic possibilities, and any other possibility you can construct as a superposition of these three possibilities. And this is a real power of field theory, of effective field theory. And these three possibilities are, the first one is massless graviton, Einstein graviton. Now, the equation for massless graviton is unique. So this graviton propagates, again, I'm already writing this equation in proper gauge. This graviton propagates two polarizations. So Einstein graviton propagates two polarizations. And second possibility, turns out, is massive, so-called Holyfield's graviton. And again, the theory is unique. There is a unique consistent theory of this sort, Holyfield's theory. And again, it has a fixed structure. different from Einstein graviton structure. So first, the first difference is that, of course, it has a mass, but the tensorial structure is also different. So instead of 1/2, you have here 1/3. Of course, coupling of massive, if you introduce Holyfield's graviton in a theory, the coupling a priori, you don't know what it is, so you have to put this parameter a of little m, little a of little m. Now, the difference is that this massive graviton propagates 5 polarizations, not 2. And this is the key issue, actually, that this is an extremely important thing. And this puts an extremely important constraint on theories of modified gravity. Finally, there is a scalar, massive or massless. Of course, you can introduce additionally a scalar, which is sourced by the trace of the energy momentum tensor. Now, strictly speaking, I would not call this a theory of modified gravity, because this is simply adding a scalar to Einstein theory. With the same success, you can say that the standard model is also a modified gravity because it contains Higgs and it contains a scalar. But anyway, sometimes people attribute this to this modification, and I'm happy to accommodate it. There are no other possibilities. So any other possibility would propagate non-positive norm degrees of freedom, and therefore is inconsistent. Therefore, at the linear level, any modified gravity theory can be represented as superposition of this. Okay, so what you call effective, your modified graviton, will effectively be some superposition. Is there a question? Yeah.
I think someone has to mute the microphone.
Is there a question?
Yeah, actually, there is a question from me because, sorry, stupid question, Gia, because 3 terms have mu indices and the last term does not.
Oh, sorry. Thank you. Must be eta mu here. No, thank you very much. I'm really sorry. I apologize.
Okay,
yeah.
I would like to ask a question here. What type of
First
argument?
one will come from with eta mu, just so that, yeah. Yes, please.
Okay, so what type of argument do you have to use to say that, for example, spin?
Yes? I cannot hear you.
You disappeared. You said spin and then no sound.
Right.
Okay, we come back to this question later, probably.
Oh, okay. Yeah, just tell me whenever your microphone is fine.
I have another question.
Yeah.
You speak about non-positive norm. Can you explain what you mean there?
Well, the basic consistency requirement of quantum field theory is that the states must have positive norm, but not every Lagrangian that you write down can consistently give you the positive norm states in the Hilbert space. And so those theories that do not give you positive norm states in the Hilbert space, therefore are inconsistent. So we call them, sometimes people call them ghosts, and so on. So those are the ones. So it turns out that, for example, if I take Einstein theory, linearized Einstein tensor, I showed you the linearized Einstein tensor, right? So you could have asked this question, I mean, why can't I modify it? Yeah, if you modify it, you will naively, you will lose this gauge redundancy, but after all, you can say, who cares? I mean, but the problem is that not that you lose gauge redundancy, but the problem is that if you modify Einstein's tensor, you will introduce precisely this type of states that do not have positive norm. And such a theory makes no sense as a field theory. And so, yeah, this is the fundamental requirement to any quantum field theory or any field theory that all these states must have positive norm.
Yeah, I know the case where the kinetic energy term gets the wrong sign. Is that what you?
That's an example of that. Absolutely.
Okay.
Yes,
yeah.
Absolutely correct.
Yeah, the question that someone tried to ask and couldn't was to the previous slide. how do you eliminate from that formula spin 1 and higher spins? So you have
spin 1 cannot be sourced by T mu nu. Here we're talking about a linear theory. T mu nu is a symmetric two-index symmetric tensor. It can only source a two-index symmetric tensor at the linear level. Okay.
Yes, but you have scalar times eta mu nu.
Right. Because
So
scalar can couple to a trace. So scalar can couple to a trace of the energy momentum tensor, and graviton, massive or massless, can couple to energy momentum tensor. But for example, a vector cannot couple to energy momentum tensor. Vector can only couple to energy momentum tensor through derivative, but then because energy momentum tensor is divergence free, this coupling vanishes.
Okay.
Okay. So the same, now the same follows, there is even more powerful argument, which follows from Cullen-Lehmann spectral representation. Because suppose you have T mu nu and tau mu nu, two energy momentum tensors, and there is a mediator between them, and there is a propagator of this mediator, okay, the correlator, H mu nu, H alpha beta correlator. Now, this correlator has a unique spectral representation. And this spectral representation has precisely the structure that it's a sum over massive poles, a massless, isolated massless pole, K is the momentum, a massive pole, a massive spin 2 pole, and a massive or massless scalar pole. These coefficients A mu square, which is modulus square, plays the role of the spectral function. Okay, so this spectral representation is unique. So any modification of this would result to a pole non-positive residue which would correspond to a ghost pole or branch cut. Now the spin 2 massive are most interesting and most problematic. Now massless spin 2, of course, it's standard Einstein. These are simply scalars. So the real modification of gravity is if you can modify the spin 2 part. Now there is an universal issue here. Okay, let me explain what it is. Now the Pauli-Fierz graviton. So Pauli-Fierz graviton, already a single one, even if you don't take superposition of those. Okay. As I said, it propagates 5 polarizations. So these 5 polarizations you can sort of split into helicities according to Poincaré representations that they would form in the massless limits. Okay. So these are 2 polarizations of spin 2 helicity. Let me call them spin 2 helicity. 1 polarization of spin 0 and 2 polarization of spin 1. So this, by the way, sort of goes back to your question, where are spin 1s? Actually, spin 1 is contained in massive spin 2, okay, as 2 polarizations of massive spin 2. However, because they do not couple to energy momentum source, and that's why I'm putting them out, because they are not relevant for this discussion. So therefore, here I'm representing massive Pauli-Fierz massive spin 2 as a superposition of would be Einsteinian part. So in other words, this would become Einstein in the limit when mass goes to 0. And then a helicity 0 component, a scalar. I will call it chi. Different people call it differently. Sometimes people call it phi, sometimes pi, whatever. Okay, I will call it chi. And now this chi enters in this form in the canonically normalized massive Pauli-Fierz graviton. Okay. Now notice that there is this derivative dependence, which is singular in the mass square. For those of you that have seen massive propagator of massive vector boson, for example, W boson, right? So it's sort of similar because W boson has longitudinal polarization, which is a scalar. And here is the same thing. So it's a longitudinal polarization of a massive spin 2. And it's singular in the mass, in inverse mass. Now this person, this chi that resides together with Einsteinian part in massive gravity, in massive graviton, mediates additional interaction, extra interaction. Why? Because it enters through, it couples to the trace of the energy momentum tensor. So it couples in the way a scalar would couple, except it's not an independent scalar. It's a longitudinal polarization of a massive spin 2. And now there is this well-known problem that Van Dam, Veltman, and Zakharov pointed out. Immediately they pointed out. They said, look, this proves that you cannot have, graviton cannot have a mass, no matter how small. We call this VDVZ discontinuity. Why? Because the way this chi enters into the massive graviton is independent of mass. For arbitrarily, for small mass, if you go from 2 degrees of freedom to 5, and one of those degrees of freedom, the zero polarization, is sourced by the energy momentum tensor. And they showed, it's easy to show, that this would give additional contribution into the deflection of light. So you see, it gives additional attraction, 1/6 times of the spin 2 part, and so therefore it would conflict with observations about deflection of the speed of light. Why? Because you have a scalar which couples differently to the trace of the energy momentum tensor, so it would couple differently to relativistic and non-relativistic sources. And correspondingly, even if you normalize your Newton's constant by measurement of non-relativistic gravity of non-relativistic sources, there is no freedom to again reabsorb this effect into redefining of the definition of Newton's constant. And correspondingly, this is ruled out. Now, therefore, this is true about any modification of gravity which contains these spin 2s, which is precisely what you would call modification of gravity, unless the coefficients are extremely suppressed. But of course, if coefficients are extremely suppressed, this would mean that you are modifying gravity, you are not really modifying it significantly at any scale. So then it would not really be useful for understanding self-acceleration, etc., etc. Okay, so the lesson from this continuity is that, what is the lesson? The lesson is that the modified gravity, if it exists, it cannot be in a linear regime already at the solar system distances. Now, this is pretty dramatic because the whole concept changes, right? Because the whole point about first Newton and then Einstein was that we could understand motions of planets and even the deflection of light by linear gravity, okay? Non-linearities were not so important, okay? However, here we are learning a lesson that if we modify gravity in such a way that linear approximation will be valid at solar system distances, this will be ruled out, okay? So somehow this tells you that modified gravity must be so smart and also so unusual that it should introduce non-linearities already at solar system distances that would somehow cure this problem of Van Dam, Veltman, Zakharov discontinuity. Now, this was pointed out by Arkady Weinstein pretty soon after they wrote a paper. So he pointed out that nonlinear corrections could cure the problem, okay? He didn't show that they cure the problem, but he just suggested because, and the reason was there was no nonlinear theory of massive gravity at that time, okay, existent. And so he just showed that nonlinear corrections are important, okay? But the idea was there that nonlinearities could cure the problem. But it turns out that there's no free lunch. Okay, at that time, actually the history is interesting because at that time, was not paid much attention to this massive gravity, etc. Now these things, and so when we wrote this model with Greg and Massimo, since our model was essentially like massive gravity, and it was fully nonlinear and generally covariant. So then Arkady told us that he had this idea before, and so the idea was to now use this theory to see if this is true. So to see whether in this theory, this VDVZ discontinuity is cured. Because in the first paper, when we wrote this model, we said there that this model was ruled out. We said that because of, unfortunately, because of fundamental Zakharov discontinuity, of course, this theory, since it propagates non-massless graviton, it's actually, we thought that it was ruled out. So we just said that. But then there was this very fundamental question, because the question is, of course, there cannot be a free lunch. If somehow your theory gives you non-linearities that are more important than linearities, linear correction, there must be some price to pay. Because always there is something happening when, in a theory, when this happens. For example, in a case of a black hole, right? In a case of black hole, it's true that if you approach horizon, non-linear corrections become as important as linear corrections. But then you have a horizon there. That's why, in a sense, the way you can understand formation of black hole horizon is one reason is that non-linearities become as important as linear corrections. But in solar system, we don't have any horizon or anything like that. So the question was, can this happen in a consistent theory? In other words, first, what is going on? How theory manages to give non-linearities which are strong as linearities? And secondly, what are the consequences? And so what we did, we analyzed this both in our model and in naive massive gravity. And we discovered immediately that there was a problem. What was the source of the problem? And the source of the problem is the following. Now, look, think in terms of massive gravity, graviton, right? Holyfield's graviton, as I told you, contains this high zero polarization, spin zero polarization. But this polarization enters in a way which is singular in M squared. Now, if you couple it directly to a source, okay, if source is on shell and is conserved, this coupling is not contributing. That's why this coupling was put aside by Van Dam, Veltman, and Zakharov. However, in self-interactions of gravitons, this is no longer zero, because in self-interactions of gravitons are not on shell. Okay, for example, in Mercury perihelium precession, they are not on shell. Okay, so therefore, what happens is that this generates graviton interaction, which is singular in M. And actually, we did this analysis because naively you may think that there are higher singularities. It turns out that all the higher singularities cancel out, and we discovered that the leading singularity is 1 over m to the 4th. So basically, there is a coupling of tri-vertex. So chi coupling, cubic coupling of chi's, of polarizations, is suppressed by the scale, which is minuscule, because Planck scale is large, but m is tiny. And so the relevant scale is this. Now, this was made extremely clear by Arkani, Hamed, Georgia, and Schwartz. They used a different language. And in their language, it's crystal clear why high order singularities cancel out and why this is the leading singularity, okay? And so why this is the strong coupling scale. But anyways, okay. So this is the conclusion is this, that there is this strong, the graviton becomes strongly interacting at this scale. Now, the question is whether this is good news or bad news. Now, for us, we took it, at that time, we took it as good news. Why? Because that was the only way to cure Van Dam, Veltman, Zakharov discontinuity. Okay? Because without that effect, the theory is simply ruled out. I mean, because then VDVZ holds. So this means somehow, but this gives you a general lesson. This tells you that any modified theory of gravity, in order to be compatible with VDVZ discontinuity, must have a built-in strong coupling. And actually it does. Okay, so it always has this built-in strong coupling. Now, the bad news is that the theory requires UV completion at a scale which is enormously low scale, okay? For example, so now the maximum, so now you can try to build theories in which this scale will be higher.
Yes, sorry, the theory, just for some people, the theory requires UV completion simply means that...
I will discuss this, yes.
Yes.
Yeah, I will discuss what it means that theory requires UV completion. But this is precisely what I'm starting now. So in other words, the point is that, okay, but first let me discuss the scale. So in other words, the question is how far you can push this scale. So here's the, let me go to the previous transparency. So here, for example, right, what happens is that if I have processes in which I have graviton nonlinearity entering, right? For example, graviton coupling, right? So this coupling will become strong. So the longitudinal polarization of graviton will become strongly interacting at the scale given by this scale, okay? Now this scale is minuscule. Why? Because the graviton mass, by cosmological reasons, I will discuss this later, has to be Hubble or smaller because of late cosmology, because we know that galaxies, they still gravitate normally, okay? And so if you plug this number, so the Compton wavelength of the graviton therefore should be larger than 10 to the 28 centimeters. That's an enormous scale. And if you plug this scale here, you will get that this scale is enormously large, okay? So therefore, already at very large distances, these gravitons become strongly interacting. Now, however, actually turns out that this is not really an actual scale, because in consistent theories, it's not this scale, but scale is a little bit different. So for example, in DGP model, the scale is pushed to a cubic root from m squared times n Planck. Ludi Porati and Ratazzi, they took a useful limit in which you decouple everything else, and you're only left with the self-interaction of chi's, and this self-interaction has this form, so it's derivative self-interaction. Okay, and the same scale appears in this model by Deram, Gabadadze, and Tolle, the same scale. But nobody, to my knowledge, managed to push the scale any further. Okay, so now this scale comes out about 1,000 kilometers. Okay, so this means that for the wavelengths of the gravitons participating in the process, shorter than 1,000 kilometers, the theory requires ultraviolet completion. Okay, so theory goes out of control. In other words, those conditions that I was using to describe gravity as a consistent low energy effective field theory are violated. So instead of becoming strongly interacting at the Planck scale, these gravitons become strongly interacting at this minuscule scale, which is approximately 10 to the minus 13 electron volts or something like that. I mean, 1,000 kilometers. This is already much larger than the scale at which Newtonian gravity has been tested, okay? So the question is what you do. So, of course, theory requires ultraviolet completion. In order to be sure that this theory makes sense, you need to have some ultraviolet completion. In other words, to understand what restores unitarity and consistency of the theory for the processes.
Yes, sorry to interrupt. Once again, I just want to emphasize for people without quantum field theory background that theory requires ultraviolet completion means simply that you have no theory, because your theory, as it is, starts to give meaningless predictions like probability of scattering greater than 1.
Exactly. So exactly, yeah. So theory perturbative. So you can no longer use. If theory becomes strongly interacting, means that quantum corrections are become become strong. In other words, they become as important and even more important than classical corrections. So in other words, in this case, for example is standard model. In standard model without Higgs boson, okay? So in standard model without Higgs boson, the scattering of WWs would violate unitarity at the scale approximately a few hundred GeV, like 700 something or 800.
Precisely because of the same longitudinal polarization.
Exactly, precisely because of the same longitudinal polarization. In other words, for instance, longitudinal polarizations of the W bosons, they become strongly interacting at that scale. And so that's why we knew that standard model, because standard model requires UV completion above that scale, otherwise the unitarity breaks down, perturbative unitarity breaks down. We knew that either Higgs or something else had to be discovered. And actually, Higgs is precisely the particle that is needed in the standard model to restore unitarity. So the Higgs particle restores unitarity. So it continues, the theory continues to be weakly interacting even above that scale. Okay? So that we call UV completion of the theory. Now, another example is given by QCD, okay? So at low energies, you can describe QCD. QCD has these degrees of freedom, pions, right? So pions are interacting with each other, and they are weakly interacting as long as you stay at distances much larger than the QCD length, approximately 10 to the minus 14 centimeters. However, if you do scattering experiments so if you do computations of scattering of pions with momentum transfer larger than that scale or approaching that scale, the coupling of pions becomes strong, and they would violate perturbative unitarity. Now in QCD we have UV completion. What is UV completion? QCD stops to be a theory of pions beyond that scale and becomes theory of quarks and gluons, and everything is perfectly fine. Now we have ultraviolet theory, which is asymptotically free and consistent. So you need something like this for this theory. But this theory, in certain sense, is infinitely harder because actually there are arguments that show that such UV completions that we have in case of standard model or in case of QCD here are impossible because this is theory of gravity. Okay, so here this requires some. So in other words, the UV completion problem here is equally severe. Actually, it's even more severe than the UV completion problem of Einstein gravity at the Planck scale. Because for Einstein gravity at the Planck scale, we have some ideas how it is UV completed, okay, above the Planck scale. First of all, it's unitarized by black holes in Transplanckian scattering, both by string theory and both in string theory and field theory. And also, we know how to compute blues, for instance, using string perturbation theory, and so on. Okay. Now here, so there is an analogous problem here, but this problem appears at the scale which is 10 to the minus 13 electron volts. Okay, so this is what is basically written here. For example, quantum effects, if I do scattering of this, if I do thought experiment, let's say I scatter these chi's, chi scattering, they become strongly interacting at that scale. Now, the question is what you do. Now, there are several levels of questions. Of course, first thing would be to really understand UV completion of the theory in order to have a microscopic theory that UV completes this theory at short distances. Now, currently, I'm not aware of any theory, any ideas. There are some ideas. I will describe them, but I'm not aware of any answer to this final answer. But then you can ask the second level question. The second level question is the following. You can say, okay, I am in the following situation. I have modified gravity. So modification of gravity, it brought new degrees of freedom. Now, these new degrees of freedom, so in other words, it has old degrees of freedom, like Einsteinian graviton, but then this Einsteinian graviton acquired new polarization, so new degrees of freedom. And it turns out that these new degrees of freedom are extremely strongly coupled, become extremely strongly coupled at very low scale, at very low distances. So imagine the following thing. You are coming from far, okay, let's say, okay, and you have a source, I don't know, sun or a black hole, doesn't matter. So you have a source, and you are approaching this source from very far. Very far, linear gravity is valid, okay? And it's like Einstein gravity, but it's order 1 different. Now you are approaching this source. At some point, there is a scale at which non-linearities become important. This is what was suggested by Einstein, okay? At which non-linearities become important. And so these non-linearities, they overshadow the naive linear computations, okay? And so what these non-linearities do, they suppress contribution from this longitudinal polarization into the classical solution, okay? Very good. So you continue to approach your source, but finally you approach your source at the distance of quantum strong complex scale. And the question is whether you can extrapolate the classical solution that you obtained in this way beyond this quantum UV completion scale, okay? In other words, you can assume that whatever is the UV completion of this theory that you need to have it completed at beyond this 1,000 kilometers, okay, will not affect the validity of the classical solution of the Einsteinian part. That's an assumption, of course, right? Now, if you work with that assumption, then you can, of course, then you can make predictions. Then you can make predictions even past this quantum UV completion scale. So, for instance, you can make predictions also beyond 1,000 kilometers with this assumption that the theory is not ruled out by UV completion, because UV completion will not affect, let's say, Newtonian law or Newtonian gravity in laboratory. If we work on that assumption, then we can make predictions because classical solutions then can be, they are tractable, okay? But again, under this assumption. For example, you can have interesting effects for perihelion precession of planets. For instance, for lunar orbit, it's pretty close to the experimental limit, okay? For instance, one could look for signals of modified gravity in perihelion precession of lunar orbit, and so on, okay? Now, the question is, finally, let me, I think I'm approaching overtime or something, yeah. So finally, the question is, are there any ideas about UV completion? So the only idea I'm aware of is the idea of so-called classicalization. Of course, I will not discuss because this requires a separate discussion, etc. But the idea of classicalization was as a sort of as an alternative to Wilsonian UV completion, that takes place, for instance, in the standard model. So the idea was to sort of have the similar unitarization of theory as black holes do, okay, in Einstein gravity. So in Einstein gravity, at very high energies, at very high center of mass energies, Einstein scattering is dominated by black hole formation. And so here the question is whether these, in modified gravity, these longitudinal polarizations, whether they could do the same. So this would mean that if I scatter, let's say 2 Chis with very high energy, instead of violating unitarity and producing very hard quanta, they instead produce very soft and very high occupation number states, which are effectively classical. Okay, so in this way, theory may somehow prevent you from probing distances shorter than 1,000 kilometers through these chi components. Okay, this is, of course, this requires to be worked out. It's unclear whether this UV completion can work in this kind of cases. Second question, interesting question is, for instance, what about black holes? What happens with black holes? Because since I mentioned that for Einstein gravity, UV completion of Einstein gravity, black holes seems to play a crucial role. at least in trans-Planckian energies. On the other hand, so the question is what happens to black holes here in these modified theories? And here there is one thing that, okay, I commented on this a long time ago, but okay, sort of a qualitative comment. So the comment is that normally the black holes obey classical. Here we're talking about classical. Classical black holes, they obey so-called no-hair theorems. And one of those theorems says that black holes cannot carry a field or hair with respect to any massive field. Now, if you modify gravity, as we saw, necessarily it involves components from, it involves projection from massive gravity, massive spin tools. And then interesting thing is that what happens with black holes in such theory? So do they eat up their own hair classically, or what happens, okay? These are, of course, all open questions. I think I'm over time. I think I should stop here, and then if there are any questions, I'll be happy to answer.
Thank you very much, Gia. Sorry, I think one very important question is that you commented mainly on this longitudinal polarization in Pauli Fierz option, but you didn't say much about the scalar, the third option.
Right, scalar is exactly the same story. I didn't say much about scalar because as far as yeah, okay, so, yeah, you're right. Probably I should have commented about it. Now the first thing is that, as I said, scalar is not really, strictly speaking, modification of gravity because you are bringing it from outside. Okay, it's a new degree of freedom, new field that you are bringing from outside. But the second thing is that exactly the same consideration applies. So, in other words, the moment you introduce a scalar will contribute in mediating gravitational force. There is a constraint coming from deflection of light, etc., on this force. And then there are two possibilities. Either you introduce a scalar which is weakly interacting, which is much weaker than gravity. For instance, Browns-Dicke type theory. Yeah, that you can do, but then the scalar will never play a major role, okay? So here, in this talk, I was focusing only on theories in which gravity can be modified by 100%, order 1 strength in infrared. So if you want to introduce scalar that does such modification, then scalar must be at least as strongly interacting as gravity itself. Then you will immediately face the same problem. The same with one-time Zakharov discontinuity, because scalar will immediately contribute. It will effectively act like a longitudinal polarization of massive graviton. And so then, if your scalar is not strongly interacting, the theory is simply ruled out to begin with, because you don't have any, it's not compatible with solar system observations. Or you have to arrange your theory to be strongly interacting. So in other words, modified gravity, if any theory in which we modify gravity in infrared by order 1 strength must have a strong coupling in order to cure Van-Dam-Veldeman-Zakharov discontinuity, okay? This looks like there is no other option. This looks like a sort of a no-go. I don't like no-go theorems, but here it looks like that's the case, okay? And so therefore, you are trading discontinuity for strong coupling. So this is universal. So that's why whatever I said here also applies to individual scalars. So the scalar doesn't have to be a component of graviton. The interesting thing about massive when it's component of graviton is that in that case the strong coupling is built in. So in that case, it's an accompanying property of the theory. So that's the interesting part. If the strong coupling is not built in, you have to arrange your theory to have a strong coupling in order to have the same Weinstein type effect to eliminate this the effects of extra degrees of freedom in the solar system. So therefore, I think it's equally applicable. Yeah.
Okay.
Does it answer your question?
Yeah, of course. So you say that either your modification cannot play a role of dark energy or anything like that, it can give only tiny corrections, do not change the picture significantly, or it will be ruled out by VDVC discontinuity, or it will have strong coupling, and then the theory is valid up to ridiculously small, only up to ridiculously small scales.
Well, yeah, that's what the picture shows. That it looks like that's the case. I personally, I've never seen any any way out of this. Let me call it dilemma. But okay, I like to take things positively. So I mean, clearly we understood several things in this framework. So we understood. I mean, understanding a problem is also an understanding, which can help us. And as I said, I mean, yeah, the theory requires UV completion at scale, which is yeah, typically is extremely low. As I told you, I've never seen a scale that is pushed higher than these 1,000 kilometers. Maybe there is something in the literature because I was not following that much lately. So this direction, maybe there is something that pushes the scale a little bit higher. Now, ideally, if you don't have UV completion of gravity, suppose you don't have UV completion, theory of UV completion, then ideally, in order not to be ruled out phenomenologically, you would like to have this cutoff of your theory to be at least in around millimeter or micron range, because those are the scales up until which gravity has been measured in laboratory. So if you have a theory which has a cutoff that is around that scale, then you can say that you are safe, at least phenomenologically, or at least at the level of effective field theory. You can say that your theory works, it is reliable. Right, so that could be another possibility. I mean, of course, there is another set of questions which are extremely interesting about, because sometimes you can have these pretty powerful tools, I didn't enter there, which tell you that already from looking at the low energy theory, you can prove, well, proving quotation marks under certain assumptions, whether a given theory can have a sensible UV completion or not, okay? So we, even without knowing the UV completion, there are very interesting papers in this direction. But this I didn't enter there, okay? So this is yet another set of questions. So here I try to be, in this discussion, I try to be maximally conservative. Okay, so to make the smallest number of assumptions and just to show you what are the most pressing, immediately pressing questions in this framework.
Okay, thank you very much, Gia. Are there more questions?
Yeah, there is a question, so. Yes?
If someone wants to ask a question, we cannot hear you.
Yeah, I just switched on my microphone. I have a stupid one. I was actually not aware that people try to cure dark energy, right? It's modifying gravity. So there's also the dark matter part, right? Where you do modified gravity to explain away the dark matter. I guess that's all free of these complications. How is that?
Right. So yeah, yeah, absolutely. There's a correct question. So the question is whether what about modifying gravity to also understand as an alternative to dark matter. There is this idea MOND. Now, I personally never worked on that. I never attempted to build any models in that direction. And the reason was that it looks like, first of all, it looks like dark matter works very well. And also, it looks like that any attempt to modify gravity at those scales to explain dark matter is even more complicated, and you have even larger number of problems. And so that's why I don't feel like motivated enough to modify gravity in order to understand dark matter. The dark energy was a different story because it was linked to this with so-called cosmological constant problem. And also, it looks like that in case of dark energy, at least you can write down a theory that has self-acceleration. So you can write down an explicit general covariant theory, which works in range of energies, which has self-acceleration. At least that is possible. But yes, I mean, it's similar, and but similar constraints apply, because you see, if you want to modify gravity, whether you want to explain dark energy or dark matter, what I said here applies. I don't see how you, if you want to modify gravity, meaning that modify something that mediates force between energy momentum tensors, one has to face all these factors. I don't see how one can avoid those factors. So probably this is exactly the same considerations will apply also there.
But also, Jan, just purely phenomenologically, modified gravity does not explain bullet cluster and systems like that.
I know. Yeah, I know. Yeah.
Yeah. So it cannot work as the only substitute of dark matter, just phenomenologically.
Yeah, that's another, right. That's another thing, right.
I'm more
Another thing,
right. I get the story, right, that you run into these this extra scalar thing that completely wrecks gravity in first instance, right? You have to do complicated exercise to get rid of it. And I got surprised, right, that apparently the dark matter modified gravity series, of course, would have the same trouble. And I guess people worked on the rock or whatever.
Yeah, so
now, right?
Yeah, so yeah, if I right, of course, as Alexei said, there are also these separate phenomenological considerations about validity of this type of quantifications. But to me, okay, that's why I try to discuss only features that are really universal. So in other words, if you want to modify gravity, a spin two part, in other words, a force between energy momentum tensors, this you have to face these problems that
I enjoyed it.
Discussing. I mean, problems or features. I mean, whatever they are. But this is very general. I mean, because it's only based on extremely well understood properties of quantum field theory, such as spectral representation, positivity of norms. I mean, the strong coupling and so on. So therefore, yeah, I mean, this is a pretty conservative set of features. So, okay.
Anyone else? Maybe from our friends astronomers?
Hi, I have a question.
Sure.
So recently there has been some talk about the observations from astronomy regarding the dark energy. So I'm not sure where things stand now with the data and how it's analyzed, but as far as I know, things seem to be a bit inconsistent. And are you taking any of this into considerations in your research, or?
Yeah, I mean, that is independent of what I said. So as I said, I mean, what I was describing here is simply, it makes no assumptions. I'm making, in this talk, I made no assumptions about dark energy. So dark energy, as I said, for us was the original motivation. Why to start thinking about modifying gravity at large distances. In this talk, I didn't refer to whether there is dark energy or not. Yeah, so it's, I mean, I think that, yeah, dark energy was so confirmed from more than one consideration. It was not only supernovae, but also CMB, and it gave, to my understanding was that it was giving a correct fit. In any case, I'm not an observer. I mean, so this is, and I don't do data analysis in dark energy. Yeah, I mean, So this is something that I'm an user. So if you tell me that there is dark energy and it requires explanation, I can try to look for explanations. So there could be one could be simply dark energy, cosmological constant, or another thing. I try to look for the theories of modified gravity, maybe. And this talk was about that. The talk was to try to understand whether what it takes to alter gravity at astrophysical and cosmological distances, irrespectively of motivation. But maybe Alexei knows more about this observational facts about these recent discussions about dark energy story.
Yeah, we have people here who know much more than me, but I agree with what you say. There are other evidences in favor of accelerated expansion of the universe. So
yeah, that's my understanding. Yeah.
Yeah, so I would not be too much worried about this fact so far, but maybe Kuhn or someone more knowledgeable than me can comment on this.
I do have a question.
Yes.
Does this modified gravity change early universe physics that can, for example, be probed by BBN?
Oh yeah, absolutely. If you have modulo to these issues that I discussed in this talk. For example, if you take our model, this DGP model of modified gravity, you can use it as a model, okay, for doing feeds, and you can see indeed. So what happens in that model is that the Hubble equation, the Friedman equation gets modified. Now, the standard Friedman equation goes as h squared equals to rho, right? And it gets modified by the term that is linear in h. So now the equation is h squared plus minus h equals to rho. And so, and h is accompanied precisely by the scale that is sort of graviton mass. And so what happens is that at early times, cosmology is normal. So it goes like normal Friedman because h squared term dominates. And at late times, the linear term in h dominates. Now, or becomes important. So now this onset of linear term, of course, is gradual. And so for example, there are constraints from Big Bang nucleosynthesis. So for instance, it looks like empirically, at least, okay, I've not done any analysis lately, but at least a few years ago, yeah, linear modification, so h squared plus h type modification of Friedman equation that was predicted by that model was really borderline of being both compatible with Big Bang nucleosynthesis and also with late cosmology. But yes, absolutely, the answer to your question is yes. If you have a model which changes Friedman equation, late times, this change will set in gradually, right, or sharply, so it depends on the model. The problem there is that we need so there must be a consistent theory, and I precisely presented a set of questions that the consistent theory must answer. Because by hand, of course, you can write an arbitrary theory. You can always write by hand an arbitrary Lagrangian, but 99.99% of these Lagrangians will give you an inconsistent theory. So they will either have very low strong coupling scale or they will have negative norms, etc. So that's why, I mean, it's very important to answer these fundamental questions before you try to test a given model phenomenologically. And this is very important to have underlying consistency of the theory that we are testing.
Thank you.
Perhaps I've yet another question. I encountered myself massive gravity in the context of holography, right, where you can actually get
yeah, people are discussing that. Yeah. Mm-hmm.
That's quite harmless, but I do remember that when you start to fool around with massive gravity, that was it that you get problems that you have to introduce ghosts, and you cannot do it always consistently. You can only pick up particular mechanisms. And in the way it pans out in holography is basically that there's tied to breaking translational invariance, right? And you're manifestly non-Lorentz invariant at the point. And then you're just dealing with purely spatial, in essence, frame fixing. That's the way it works.
Okay.
And I guess when you do that you can get basically around all these difficulties, right? Because you break Lorentz invariance badly, and this problem is the deflection of light may disappear. Is it correct?
So yeah, I should mention this connection that, of course, here I was assuming that the space-time curvature is not much higher than graviton mass. Okay.
Yeah.
So for instance, here I was working in asymptotically Minkowski space, but in any case, these conclusions are valid if the space-time curvature is not much higher than graviton mass. Now, if space-time curvature is much higher than the graviton mass, then the story, of course, becomes different, because already at linear level, for instance, to have a massive spin 2 in de Sitter space, okay, you have this so-called Higuchi bounds, etc. So there are certain windows that are allowed for massive spin 2, and also in anti-de Sitter. So there the story changes. So in those cases in which the so-called graviton mass becomes subdominant to curvature, or then you have to even linear theory has to be reconsidered. Okay. Now I was not going there because since, as I said, since this original motivation was accelerate expansion of the universe, so in our universe, because of obvious reasons, the graviton, in order to have anything to do with acceleration, this pole, you know, in graviton propagator should be around the Hubble. Okay, so it cannot be much higher because of obvious reasons, because the galaxies they gravitate normally, and cannot be much lower because then it would not be relevant. So therefore, yeah. So therefore, these considerations they are are different. But I agree, yeah.
I start to reconstruct it, right? It's a really different angle. So it's rather easy to figure out that when you break space translations, right, you will acquire a graviton mass. Under the condition, of course, that when you break translational symmetry, you can only break space translations because you cannot break time translations, right? And therefore, it's automatically very non-Lorentz invariant. Right now, in that case, it's all space-like, and it's okay because this is a physical act, right? That could happen, and it's series consistent. When you want to use it for, say, dark energy purposes, you're interested in the time parts of it, right?
Yes, in other words, indeed.
You cannot break time translations, and therefore this route to consistency is blocked.
Right. So yes, indeed. You see, indeed, as you said, if you have a source that breaks space translations, in certain sense, we can say that the source generates mass for a graviton, because you sort of have a gravitational Higgs effect.
Yeah.
Because you are breaking translation invariance spontaneously, and the corresponding Gold would be Goldstone mode, the sound wave.
Exactly.
Mixes with graviton, right? Now, that's absolutely correct. So therefore, the similar thing will happen if you have a normal dark energy. So if you have normal dark energy, let's say quintessence, right? People are discussing the scalar field that is slowly rolling. So quintessence, for instance, could break if it's inhomogeneous, it could break space translations, and that would generate mass to a graviton. Now, this is not the type of mass I was discussing. I didn't want to break space translation invariance. I wanted to get self-acceleration. Originally, at least, we wanted to get self-acceleration within Friedmann equation, which only depends on time. Okay, time-dependent, space uniform Friedmann equation. And the way our theory was doing that, modulo problems of these, and then there were other problems also, which I didn't enter to, about negative norm states on those branches. But the idea was that if you have Friedmann equation, which is non-linear in Hubble, then you don't need a source. So it can have a zero for non-zero Hubble. So the Friedman polynomial in Hubble can have a zero for the value of the Hubble, which is constant but non-zero. And that would give you a de Sitter-like expansion, even if you don't have any source. And this is what was happening in that theory. So in that theory, basically, you had h squared minus h, and you don't need a source, because h squared minus h has a solution with h constant, even without any source. So it was a different type of self-acceleration. So it was without breaking translation invariance.
Yeah.
But I fully agree, yes, translation invariance, effectively you can think of it as generation of graviton mass. Yeah.
And yet again, right, you break Lorentz invariance badly because you cannot break time translations. It's impossible.
Well, I mean, the background can break Lorentz invariance.
The time crystal thing.
Yeah.
There's no way you can, consistently quantize it, blah, blah. It's a disaster when you break time translations.
Of course, yeah. So the thing is that you cannot break time translations. You cannot break time translation by a background which is, but you can break. But this given state, of course, may not be time or space translation invariant. Any state that carries energy, right?
But it's basically periodicity, right? It's a time crystal thing.
Yes, exactly right.
Right, and that is really forbidden. You're not supposed to touch it, even though you are like a relativist, right? And then it gets simple because spin 2 means strictly spatial spin 2. You lose the Lorentz invariance, right? You only break translation in space section, not in time. Right? It forces you to be deeply non-relativistic, right? And they have pure spin 2 space translation, spin, and that's talking to shear, spatial shear. And the whole time axis falls out, right? And you cannot do anything like, cosmic acceleration and so forth.
Yeah, I mean, you are bringing an important issue. And so there were papers, for instance, trying to understand modification of gravity by breaking Poincare invariance in the theory. Okay. Either spontaneously by certain background, or even by hand. Simply you take theory which is not invariant,
simple, right? So
which is not Lorentz invariant. I didn't enter there because it looks like that those theories have another set of problems.
Yeah, but
which are another set of problems. So correspondingly, because you see, the point is this: in Einstein's gravity, GR, Lorentz invariance or Poincare invariance is a property of a particular background, Minkowski background, which is, of course, very important background because it's a correct S matrix vacuum. Minkowski is a consistent S matrix vacuum. So therefore, of course, it stands out, but still, it's a property of Minkowski vacuum. So in other words, what Einstein theory is telling you that if you break Lorentz invariance by a state, if you have a state that is not Lorentz invariant, okay, transforms under Lorentz boost, the same state, because it has energy and has momentum, if it breaks, it also will contribute into the curvature. So your background produced by that state will no longer be strictly Minkowski, okay? Now, the point is that if you want to disentangle the two, if you want to have a theory which on one hand produces a flat background, but at the same time, dispersion relations of particles on that background are not Poincare invariant or Lorentz invariant, I don't know if such a theory can even be consistent, because there are other sets of problems that I didn't discuss in this talk, etc. But that's a completely different game. Okay.
So what I'm saying, right, is it's way simpler. You just assume that all the matter in the universe is a crystal, right? So the universe is filled with one big rock, and you just solve standard Einstein equations. And the outcome is, right, it is a spatial massive gravity theory.
No, I understand, but the solution has to be self-consistent.
So matter comes first, right? And matter has capacity to break symmetry. And when you break translational symmetry, right, you automatically complete the Lorentz invariance because you cannot make time crystal. Right? And
no, but wait a minute. I mean,
no, that's very consistent. I mean, so Einstein theories say, better only.
No, you need a theory for that. You should.
Sorry, gentlemen, we still have 26 people here, so maybe discussion you can do.
It matters, Alexa. It matters. You guys don't know you can do better physics. Crystals form regardless whether you have gravity or not. they come first, and they're a big force in the universe, right? Now the issue is very simple, that crystals are extremely rare in our universe, right? It's all dust and gas and radiation, blah, blah. But you can ask the question to Einstein's theory without modifying anything about Einstein's theory whatsoever. Your matter source is just different, of a different kind. You get a different universe. But that's by itself internally consistent. It's not a universe we have, right? Because there's no such thing as a big rock filling our whole universe.
Yeah, we can discuss that. Yeah.
What kind of you wish to have.
These are interesting questions. Yes, absolutely.
Yep.
Okay, yeah, we are already 30 minutes over time. So those who wanted to leave, they are already left. Maybe there is one or two short, urgent.
I'd like to say that I'm putting up a recording of the first and the third lecture on the website.
Yeah.
Soon, for people.
Okay.
To watch it back.
Okay, if there are no more questions, Gia, thank you very much again. It was really very, very clear and informative lecture, at least for me. I enjoyed it a lot. Thanks a lot.
You.
Yeah.
Okay.
Okay.
Thank you very much. Okay. Bye.
Bye-bye.
Bye.